Well, hello again. I wanted to pick up where we left off last time and start talking about vectors and comparing them with scalars. If you're following along in your textbook, that's chapter 2 we'll be working on. One quick note that what I'm writing here on this page, if it's hard to see in the video, remember I've posted a PDF. I've scanned in at the end what I've written, and I've posted that PDF on my website, and I will put that link to the website in the notes on this video. So you can get that and look at it as you watch the video, or if you see something you can't quite see in the video, it's usually a little bit clearer in the PDFs. Well, let's go ahead and get started. So when we talk about vectors and scalars, let's compare those. I'll start out with a scalar. Maybe we better put a title here. So if we talk about scalars, a scalar is something that only has a magnitude. Okay, and a vector then has both a magnitude and a direction. It has both of those. If it doesn't have both of those, you haven't answered the question. So it's important when you're asked to give the answer in vector form, you give both magnitude and direction. You give both of those pieces. If we look then at examples of these, a scalar, good examples are time is a scalar, volume, mass, density, speed. Speed is a little bit confusing because if I look over here as a vector, velocity is a good example of a vector. Speed is really just the magnitude of velocity. Of course, if you're looking at your speedometer, you really have no idea what your direction is. So speed is a scalar, only has a magnitude, whereas velocity has a magnitude, that being speed, and it also has a direction. Other vectors, distance or displacement, position, if you will. Of course, we differentiate velocity, we get acceleration, and force, and that's why we're talking about this. We're going to be using a lot of force vectors. So those are some examples of scalars and vectors. Let's talk a little bit about the nomenclature and symbology and whatnot. If you're reading along in your textbook or you're looking at printed material, you'll usually see a vector represented in bold. Okay, nice bold type. I don't think anyone wants to watch me make vectors bold. That's a little bit slow and whatnot. So what I'm going to do is instead I'll put a little vector hat over it. That's pretty standard, a little arrow. Some of the things that you may see other people do, they might put a double back on it, or maybe they'll put a little hat on it, or sometimes they have a dot. I would try and avoid these because those usually have other meanings in math and engineering. So I'm going to try and avoid those and stick with, if we have printed material or in your textbook, you will have something that is bold. And if you have, if I'm writing it out, I'll put a little arrow over the top of it. Now this is important that we do this because certainly this and this mean two entirely different things now. This is a vector, whereas this would be the magnitude of the vector, or we would say that this would be the absolute value of that. So if we omit the vector hat, unless we're talking, there's some spots in dynamics where we do this in context and everyone knows it's a vector, so we don't get too worried about that. But strictly speaking, unless we have an agreement like that, if we write this, we're not talking about the vector, we're talking about the magnitude. So a few things to think about. Let's talk about different types of vectors. There's different types of vectors. The first one maybe we'll talk about is a free vector. And a definition of free vector is not confined to or associated with a line in space. Okay, an example of that, let's say that we have a body that's not allowed to rotate. This body's not allowed to rotate, and whether we apply a force right there, whether we were to apply the force right there, we could call this, maybe we'll call this F2 and this F1. If as long as those forces were the same in magnitude, they would have the same effect on that. And this will probably make a little more sense as we talk about a sliding vector or we talk about a fixed vector. A great example of a free vector is a moment. Okay, a moment, which is really a torque, we'll call it a moment. We'll get into that a little later in this term, but we'll come back and we'll talk about moment being a free vector. That's going to have certain implications, so you'll hear that term again. Well, if it's not a free vector, you got a couple other choices. We could talk about a sliding vector. A sliding vector is a vector which a unique line in space must be maintained. Okay. Sliding vector is a vector for which a unique line in space must be maintained. So an example of this, and this really leads into transmissibility. And you're either used to in previous editions talk about transmissibility. It's not in this edition. But the concept is fairly easy. Let's say that we have a body or gadget or widget or something like this, and we have it supported on a roller here, and then we have it pinned there, and I have this line. If I'm looking at the internal reactions, the external reactions, not the internal forces, but the external reactions. So I want to find the reaction here, I want to find the reaction at the roller. Whether I apply that force here or whether I apply that force there doesn't make any difference. It only has to maintain that line in space. A little bit like if your car runs out of gas. Whether you push on the back of it or pull on the front of it, you will probably cause the same reaction. So it only has to maintain this line in space, and this is the concept of transmissibility. The last vector type and the most restrictive is a fixed vector. Which has a unique point of application. Okay, has a unique point of application. So those are three vectors. We've got the free, the sliding, and the fixed. You don't want to concern yourself too much with this. You can do a lot of good vector work and never really use this terminology, but when someone comes along and talks about a free vector or a fixed vector, I wanted you to understand what's going on, and a lot of this will probably make more sense as you start to work problems with vectors and get to practice this. Well, speaking of working problems with vectors and whatnot, let's get started with that. Let's say that we take a couple of vectors. Maybe we'll take a vector F1, and these could be acceleration vectors or velocity vectors. I'll talk about force vectors, which is probably more applicable to what we're going to be doing here. So I'll take vector F1, and let's say that I have vector F2, and I'd like to add those together. So I would say that the resultant vector would be equal to F1 plus F2. Okay, there's a couple ways to do that. Certainly graphically, we could take this vector F1 and we're going to add it then tip to tail. We take this vector F2 and put it down here, and we have something like this, F2, and you're going to then, adding those tip to tail, you will get the reaction vector F sub r. Okay. There's a couple ways that you could think about that if you did it like that, or sometimes they'll do it with the parallelogon or the parallelogon rule. We've got F1 here, and we've got F2 there, and we could complete the parallelogon, and there is our F sub r. Okay, so a couple ways to think about that. You could always do it graphically. If you had a scale and protractor and whatnot, you could do that. We're probably going to talk about other ways because you don't necessarily want to carry around graph paper and a scale and things like that. If you're doing it on a program like AutoCAD or something, that's actually how it draws, is using vectors. So it's going through this. If you wanted to subtract them, what if we wanted to take that the resultant, we'll say Fr prime is equal to F1 minus now F2. What's that look like? Well, let me rearrange that mathematically a little bit and say that that would be F1 plus a minus F2. I should be able to do that. And what does that look like? If I take this, and maybe I'll use this one here. There is F1, and here we had what? We had F2, didn't we? So if I flip this, I would have, there is minus F2. It's pointing the opposite direction. And I could say then, adding those tip to tail, that this is F sub r prime. Okay? So you can add vectors, you can subtract vectors, and subtracting is really just adding the negative graphically. Let's talk about some things that we will need to do, review, and be comfortable with as we start to try and introduce a little bit of math into this, so we're not just stuck with a graphical representation of this. So we're going to talk about a coordinate system, initially a two-dimensional, an x system, or a x-axis and a y-axis, and we're going to give a unit vectors. We're going to talk about the unit vector I and j. Those are unit vectors. And probably a lot of you are taking Math 254 at this time. You're getting a lot of this same information in a little different context. You'll recognize, if you don't already, that unit vectors really just represent a direction. They do not have a magnitude. Well, I should say their magnitude is 1, so their magnitude does not change anything, and they really only represent direction. So we talk about the I unit vector in the x direction. We'll talk about the j unit vector in the y direction. So if I take and I apply a vector here, or have a vector here, let's say this vector f at some angle theta here, I could say that it has a component in the x direction and has a component in the y direction. We could talk about this as the f sub y, and this as the f sub x, the x piece and the y piece. So summing up what I've got there, I could say that f is really equal to fx plus fy, couldn't I? I mean, if you believe in adding vectors tip to tail, if I add this fx to this fy, I will get that f. Well, I could write that in with the unit vectors. I could say this magnitude fx. So I'll write that with the magnitude, and then I'll give it the direction in the I direction. Plus, I'm doing the same thing with the y. There's the magnitude in the y direction, and the unit vector in the y direction. We've got something like that. So we'll eventually extend this into 3 dimensions, and we will add to this the k unit vector in the z direction. Let's talk a little bit more about fx and fy. We really just have a triangle here, don't we? Where we've got the hypotenuse is the force F. We have fx over here, and we have fy there, a right triangle. There is theta. So we can say fairly easily that the magnitude of fx is equal to f times the cosine of theta, whereas the magnitude of fy is equal to f times the sine of theta. Now be careful, don't always think that x is cosine and y is sine, because if someone comes along and defines this angle in here, then you're going to either have to switch that angle or recognize that these trig identities will change on you, or the identities that you use will need to change. So those are the individual components. What if you wanted the magnitude of this thing? Well, the magnitude, which would be, we could write it like that, or we could just write it without the vector hat on there. That's the distance, that's the length of the hypotenuse. We could use the Pythagorean theorem on that. We'd have the square root of fx squared plus fy squared, like that. Now, what if you wanted this angle? Let's say we're given fx and fy and you wanted that angle. You could say then that theta is equal to what? The arctan, the arctangent, inverse tangent, however you want to do that, of what? The opposite side, so it'll be fy over fx. Again, looking at this right triangle. Okay. So those are some identities, certainly some review and whatnot as we try and go from a Cartesian form. Isn't this a Cartesian form? A Cartesian form to one where I have a magnitude and angle, which we say is a polar form. Okay, so we'll talk about a Cartesian representation, which is what we have here, or we could talk about and really this is the Cartesian representation with the unit vectors, or we could talk about a magnitude angle representation that we'll usually talk about as polar. Well, let's put some of this into use. Let's look at a couple of examples. So, with the examples here, let's say that I have something like this. And we've got some sort of a bracket here. And we're applying a force to here. We've got this that is 600 pounds. And we've got this one horizontally that is 800 pounds. We're told a few things about here. We're told this angle is 60 degrees. We're told that this distance here is 6 feet. And I haven't drawn this to a very good scale, trying to make it so I could see the writing in here, but this is 3 feet, so my scale is a little bit off on this. Okay. So what we would like to find then is I would like to find the resultant force. Okay, I'd like to find the resultant force. Well, the resultant is really a fancy way of saying sum. I'd like to find the sum of those. I'd like to add that 600-pound force to that 800-pound force and see what we come up with. And I'm going to approach this a couple of different ways. I'm going to approach it from a geometry standpoint. I mean, we could do it with a graphical. We could get out some graph paper and a protractor and whatnot, or we could throw it into AutoCAD, and that'd be fine. You could check that out. But I'm going to, on the paper here, I'm going to use a geometry approach where I'll probably draw a figure and then aid that with law of sines, law of cosines, and then I'm going to go with an algebraic approach. So let's look then at the geometry solution. So let's see. So the geometry solution is going to look like this. We're going to add these tip to tail, right? So I'm going to take this 800. There's 800 pounds, and I'm going to add it to the 600. That's directed down like that. And I know the resultant is going to be right there, isn't it? So there is the resultant. Now we're told that this 800 is horizontal, so I know that that's horizontal. And then I need to come up, I guess I need to come up with that angle in there. So maybe I'll call that alpha. And if we look at our work here, that would be that angle in there, wouldn't it? Which, from geometry, we know is the same angle there, isn't it? So I have to spend some time trying to find alpha, won't we? So if I look at this, I could say that I have a triangle here. I look at this triangle that's made right there. Where this distance here is going to be that distance there. That's going to be what? 6 times the sine of 60, isn't it? I've got this side here that's 6, so this is going to be 6 sine of 60. And then this side over here, which is from here clear over to there, across there, right? So this is going to be 3 plus, and then I need to add that little piece to it, don't I? Which is going to be what? 6 cosine of 60. Okay. So I could say then that this angle in here, alpha, would be equal to the arctan, the inverse tangent, of the opposite side, which is 6 sine 60, divided by the adjacent side, which is 3 plus 6 cosine 60. Okay. And if you run through the math there, that turns out to be 40.9 degrees, or you could call it 41 if you wanted to. 40 degrees in there. And like I say, I've drawn this a little out of scale, so I think if they were to draw this to a better scale, it would look closer to 45, so I think that seems fairly reasonable. So that's the angle in there, which has to be the angle there. So we now know that angle, don't we? So I could come up with this, the magnitude of f sub r, which would be equal to, and I'll write this for a while like this, eventually I'll stop writing this, but the magnitude is going to be by the, law of cosines. We would have 600 squared plus 800 squared minus 2 times 600 times 800 times the cosine of the included angle between those two sides, which is that 40.9. Okay. Now, if you're rusty on your law of cosines or your law of sines in Chapter 2, your author talks about those. Remember also Appendix A in your textbook has a lot of math review in it, and some identities and things like that. So use those to your advantage. But when you go through this, let me double check this here. Yeah. When you go through this and the smoke clears on this, f sub r, the magnitude of that is 523.8. We'll just call it 524 pounds. Okay. If you go through a unit analysis on this, you have pounds squared plus pounds squared minus essentially pounds squared, because this is unitless, and under the radical, then that comes out as pounds. So hopefully those units make sense. Now, the last thing we probably need to do is, if I answer what's the resultant, it is a force, it's a vector, so I'd better get a direction on this thing. So let me put an angle in here. I could call that theta, We could use then the law of sines. So with the law of sines, we could say that 600 was to the sine of theta as what? F sub r, our 524 that we just found, is to the sine of 40.9. And this turns out then, theta turns out to be equal to 48.6 degrees. You'll notice that I try and keep 3 significant figures in most of my answers, which works pretty well. So 48.6, 524. So we know if we were to answer this that f sub r is equal to 524 at an angle of 48.6 degrees. Now, is that a proper answer? Not necessarily, because if I give this angle here, I usually assume it is measured positive counterclockwise from the x-axis. So if you don't say anything else, they're assuming that you're measuring it like that, which is not our case. We're measuring it down like that. So we could come and find the complement of that, or it's probably just easier to draw a little picture of it. There it is right there. We'd also want to make sure that we put our units in there. We've got pounds, and now we have a proper answer. Well, let me come back and do this. This was the geometry approach. Let me try it with an algebra approach. So we'll go to page 5, and okay, so there's our problem. We'd like to look at doing this with algebra. And I'm not going to show you both these methods to try and give you something that you can pick and say, hey, I want to always do it with algebra, I always want to do it with geometry. The good news is no matter how you do it with algebra or with geometry, as long as you don't make mistakes, it's going to be correct. It's not, if you did a problem with geometry, then you might get the wrong answer with algebra. That's not true at all. But sometimes a problem is much more difficult with an algebraic approach than it is with a geometry approach. Probably not so much in this problem. We're going to do a problem pretty soon where you'll see a significant difference in the degree of difficulty. Well, first thing we need to do in the algebra approach is we need to sum up the pieces in the x direction and the y direction. So if I sum up the pieces in the x direction, I'll go ahead and take a positive to the right. That 800, that's all x, isn't it? So I can say that I have 800, that's positive because it's to the right. Okay, and then this, does this 600 have an x component? Yeah, it does. I mean, if we look at that 600, there's that 600, and there's this angle alpha in there. So you still have to find alpha, no matter whether we use the geometry approach or the algebra approach. You still got to get alpha in there. So we're going to then subtract off 600 times the cosine of 40.9. That's that alpha that we had in there. Is that right? Yeah, that's that piece right there. It's going to the left, so we're going to subtract it. Before we grab the calculator, if I sum up the forces in the y direction, I'll go ahead and take positive up. We wouldn't necessarily need to, but we'll be consistent. We'll take positive up. Does this 800 have a y piece? No, it doesn't. So I'll put down 0 there. And this y piece is pointing down, so I'm going to have to subtract off then 600 times the sine of 40.9. Okay? So grab your calculator, the math on this, and I would encourage you to actually grab your calculator. Hit the pause button, grab the calculator, and bang these out. Make sure you're getting the same number. Make sure your calculator's not stuck in radian mode or something like that. You don't want to find that out on the examination. So grab your calculator, work along on this. This should come out to 346 pounds, 346 pounds, and this one's going to be minus 393 pounds. So with that, I could write this in Cartesian form if I wanted to. Take these and say that f sub r is equal to 346 in the, there's the x, so 346 in the I direction minus 393 in the j direction, and that would be pounds. That would be a proper Cartesian answer, but it's hard to compare. I mean, we've got this answer here we're trying to compare it to, aren't we? Well, we're comparing apples to oranges, so let's see if I can convert this answer here into a polar answer. And the way we do that is just put it on an xy coordinate system. So there is x, there is y. We said we went out 346 in the x, so there is 346. We went minus 393, so there's minus 393 in the y. And we have something like that, where the resultant is sitting in there like that. This is looking good. It looks like we're at least in the right quadrant. So I could say that the magnitude of f sub r is really the square root of what? 346 squared plus a minus 393 squared. And eventually, when I write that, I'll just write 393 squared, because everyone knows when we square it, the negative sign goes away. Yeah, hammer that on the calculator. You have 524 pounds. That's a number I like. It's looking good. And then we need to find out this angle here. Let's again call this theta. So we could say that theta, and I'm starting to look at this now as just a triangle. Instead of hassling with the negative signs and whatnot, I always just come over, look at this as a triangle. This is 393. This is 346. Okay? And we just look at our trig identities. We could say that this is the arc tangent, the inverse tangent of the opposite side, which is 393. Made a hash of that. 393, that's the opposite side from that angle. Over the adjacent side, 346. Okay, I'll just draw the triangle and I don't have to worry about the negative signs. And you go through the math on this, and it turns out to be 48.6 degrees. So again, we could write that f sub r is equal to 524 pounds at 48.6 degrees, and again I'd need to include this drawing like that, and we see that compares favorably with that. Okay, and again, I don't show you both of those methods so that you can pick one, say I'm going to be a geometry expert or I'm going to be an algebra expert. It's just that some problems lend themselves well to one or the other. Certainly in a problem like this where it seems really very similar in terms of complexity, doing it both ways is kind of nice to get some verification of the answer. Well, let's try one more problem for the day. And this is a problem where one method is probably going to be significantly easier and the other one more difficult than the other. So let's say that we are given this situation. Maybe we have a box or a crate or some sort of an object sitting on a surface, and we apply two forces to it. We'll say that this is P is equal to 100 newtons. I guess we'll use the metric system here. And we'll say that Q is equal to 200 newtons. This is some angle down phi, and this is some angle up. We'll call that theta. Okay? And we're told that the resultant of P and Q is horizontal. Let's see, is horizontal to the right. and 250 newtons. Okay, so this one we're kind of told the answer, and we're asked to work backwards and essentially find out where these forces are applied at, what the angle theta is and what the angle phi is. We're told that the result is in the horizontal direction, so there's the horizontal direction. It's to the right, and it's 250 newtons. Okay, so let's see if we can do this. A little sketch of what we have going on then is we have this one added to this one, and they come up to that. So let's see, we've got the answer then is this horizontal at 250 newtons, and to get there we've taken the Q vector like this. There's Q at 200 newtons. There's the angle phi, and we add that tip to tail to P, which we said was 100 newtons, and I haven't drawn this to a very good scale. You could scale it out if you wanted to. But this angle in here would be the same as that angle in there, wouldn't it? So we have theta in there. So we're set up nicely with this diagram, and even if we were to do the algebra approach first, this diagram might be kind of handy. But since we've got this diagram here, let's look at the geometry approach. Okay, so with the geometry approach, I could really say, using the law of cosines, that if I wanted to find what, theta, so use law of cosine to find theta. Okay, so I'm going to use this as the side opposite the angle there. So I could say that I have 200 is equal to the square root of 100 squared plus 250 squared minus 2 times 100 times 250 times the cosine of the angle between those, which is theta. So you go ahead and work through this and find that theta turns out to be equal to 49.4 degrees. You could start by squaring both sides, and then you'd subtract off those two pieces and divide by those, and eventually you would come up with theta. Now we could use what, law of sines, and say that 100 over the sine of phi, 100 over the sine of phi is equal to 200 divided by the sine of the angle we just found, theta, which is 49.4 degrees. And with that, then, phi turns out to be equal to 22.3 degrees. Okay? So grabbing your calculator, going through that, you should come up with those. Now that was fairly easy, hopefully fairly easy. We got some answers. Those are our answers. Let's check them out with the algebraic approach. So if I look at the algebra approach, what are we going to come up with? That was fairly easy, so that must mean the algebra approach is the one that's not particularly easy. You're probably right. Well, if I assign an xy coordinate to this thing, there's x, which is in the I direction, there's y, which is the j direction, and I could say then that I have the vector p plus the vector q is going to be equal to, we said it was horizontal, magnitude 250, so it'll be all in the I direction, and it'll be positive, right? So we'd have something like that. Now I could break this up if I wanted to. I could say that P is really equal to 100 times the cosine of theta in the I direction plus 100 times the sine of theta in the j direction. Is that going to work? Yes. And then Q, similarly, is 200 times the cosine of phi in the I direction plus, not plus, it's It's going to be negative in the y direction, isn't it? So I'll have negative 200 times the sine of phi in the j direction. Are we right with that? That's positive, this is positive, and then that's negative. Yeah, 100 cosine theta, 100 sine theta, 200 cosine phi, minus 200 sine phi. Yes, this should be good. So, if I equate i's and j's then, so equating like components, so for I, what am I going to come up with? 100 cosine theta plus 200 cosine phi is equal to what? 100 cosine theta, because I'm really just in this, I'm really just substituting these into that expression there. So I've got the I piece, 100 cosine theta, 200 cosine phi, and that equals 250, doesn't it? Okay, so there's one equation. Then for j, what do I have? Well, I'm going to have 100 sine theta minus 200 sine phi is equal to, there's no j in the, no j over there, is there? So that would be equal to 0. So with this, I have what? Two equations and two unknowns. Okay, so that's what you live for in math. Two equations, two unknowns. We should be able to solve those. Well, we'll keep this handy. We'll probably come back to it and see what we can do with that. So starting with those equations, I'm going to take this second equation right here. Okay, keep track of these. I don't want to end up substituting it into itself later. So I'm going to use that equation right there. And so I'm going to say then that I have 100 sine theta is equal to, moving that to the other side, I'll have 200 times the sine of phi, right? So if I square divide both sides by 100, I have sine theta is equal to 2 sine phi. Now if I square both sides, sine squared theta is equal to 4 sine squared phi. And let's see, subtract 1 from both sides. Sine squared theta, sine squared theta minus 1, subtracting 1 from both sides, is equal to 4 sine squared phi minus 1, right? Well, what do I do with that? Well, I could recognize, I go over here to trig ID. This is a pretty common one. Sine squared, let's say theta, plus cosine squared theta is equal to 1, right? The equation of a circle. Sine squared theta plus cosine squared theta is equal to 1. So I could say that sine squared theta minus 1 would be equal to minus cosine squared theta, rearranging that, right? So sine squared theta minus 1 is equal to minus cosine squared theta. So I'm going to substitute that in because I've seen that before. So I sub that back in over there, and I can say then that I now have minus cosine squared theta is equal to 4 sine squared phi minus 4. Did I do that right? Yes. So minus cosine squared theta is equal to 4 sine squared phi minus 1. So solve for cosine theta. I've got cosine theta is equal to the square root. I'd take the negative to the other side, so I'd have 1 minus 4 sine squared phi. So cosine theta is equal to the square root of 1 minus 4 sine squared phi. Well, let's see. I think it's time to use this other equation. Going back over here, now we have this one, don't we? I'll draw a box around it. Okay. I've got an expression for cosine theta in terms of phi. So when I substitute that into there, okay, so I'm going to substitute into that one right there. We'll see what we get. So maybe I'll be a little more complete with this. Now take our equation, that one that I circled or put a square around over here. We've got 100 cosine theta plus 200 cosine phi is equal to 250. And I'm going to substitute that into there, so I get 100 times the square root of 1 minus 4 sine squared phi plus 200 cosine phi is equal to 250. Let me double check, make sure I'm on the right track there. 100. Yeah, I think I'm okay with that. So I took a little pause there because I wanted to double check that. This is a good point to take a pause, because while it looks like we've made a uglier equation, we've actually made things a lot better because we only have one unknown. We can then solve this thing. For phi. We've got one equation here now with one unknown, phi. We can solve that for phi, and quite a bit of algebra in there. Yeah, you know, I would start by dividing everything by 100, and then you're probably going to want to square things out. So you've got quite a bit of work to do there. But when you do that, you're going to come up with phi is equal to 22.3 degrees. So that's good news, because I think we recognize that from over here. 22.3 degrees. Now we could grab either one of these equations here. I'd probably grab the easier one, the circled one down here. So I take a 100 times the sine, down there, 100 times the sine of theta minus 200 times the sine of phi is equal to 0. So we put this into there, and we'd solve for theta, and theta then, therefore theta, turns out to be equal to 49.4 degrees. Have we seen that before? I think so, 49.4. So again, I don't think this is the easy method. This is the hard method, going and sorting out, finding which trig identity that you want to use. Why would you all of a sudden square both sides and then subtract 1 from both sides? If you're on an exam, those are hard things to all of a sudden think of when you're under time and stress and things like that. So this problem, I would definitely encourage you to use the geometry approach, and hopefully reinforce the concept that you don't want to just stick with one approach, that you want to be able to do both approaches, because as you can see, you get the right answer, but one can be quite a bit more difficult than the other one. So I think that's it for today. When we get together with the next lecture, we're going to add another dimension to this, the z dimension, the third dimension, and start looking at problems in 3 dimensions. So that should be fun. Thank you for listening, and take care until then.